In this section, we're going to look at methods for inverse Laplace transforms and convolutions. With the inverse Laplace transform, the basic idea is we're going from a function in the S domain, the Laplace transform domain, and we want to go back to the t domain. We want to find the function of t that has that function for its Laplace transform. As we have seen earlier from the few examples that we've already looked at in this chapter, that's an important part of the process of solving differential equations when we're using Laplace transform methods. I thought it would be useful here to give a quick overview of the chapter. In the first section, we looked at the definition of the Laplace transform, the linearity property, the operational property, and looked at some simple examples. In the previous section, we looked at some more complicated properties, things like the first and second shift property and a couple of other things. And that allowed us to greatly expand the vocabulary of functions of time for which we can find the Laplace transform. We know that there's a lot of different kinds of functions in general that we deal with in solving differential equations. So that was a pretty significant step in our process of learning about Laplace transforms for differential equations. Now we know how to find the Laplace transform of quite a wide variety of functions. In this section, section 3.3, the main idea is going back from a known function of s to a function of t that has that function of s as its transform. And there's two main ideas here. The one key idea is the idea of partial fractions, which we've already encountered a little bit in an earlier example in this chapter. We also did a little bit of work with partial fractions in connection with some of the separable differential equations that we looked at earlier in the course. So the technique of partial fractions is going to be a very important piece here. I'm not going to be going through much of that at all in this video because I'm hoping that there are enough examples in my book, and I would highly recommend folks study those examples carefully. A lot of different variations on that idea of using partial fractions to invert Laplace transforms. And another piece also in connection with that is the idea of completing the square. If you don't already have a perfect square, that will be one of the baby steps in that process. And again, there's a lot of examples in my book, so I'm not going to be going through that type of thing here in this video. I'm mainly in this video going to be focusing on the definition of convolution, look at some examples and properties of convolution. And once we convolution is something that can be used to invert Laplace transforms, and it also has many other interesting properties, as we'll see. Once we have this material in hand, the last thing we'll do in this chapter and the next section is kind of pull everything together and look at Laplace transform solutions of a lot of different kinds of differential equations. So for starters, here we're going to have the definition of convolution. This may look a little funny if you've never seen anything like this before. The notation that I'm using is fairly standard, although you may see slightly different notation sometimes in other books in applied mathematics or engineering. But this notation is fairly standard. Notice tau is my integration variable here in this definition, and when I integrate with respect to tau, I end up with a function of t. So to start getting comfortable with this definition, before we do anything else, it hopefully will be useful to just look at an example and just work through that calculation in some detail. So exercise 9E is a problem of that type where I give you two functions, f of t is t and g of t is e to the 2t, and I ask you to find the Laplace transform of the convolution of those two functions. So here we go. The first thing I do is I just plug into the definition in the orange box on the left. If f of t is t, then f of t minus tau is t minus tau. If g of t is e to the 2t, then g of tau is e to the 2 tau d tau. So this expression is just immediately plugging everything into the definition of convolution in the orange box on the left. So once we can calculate this integral, we will have the convolution of those two functions. The idea for the integration here is we're going to do integration by parts. Keep in mind we're integrating with respect to tau. So if we let u be t minus tau, du is going to be minus d tau. And if then the rest of it, dv, e to the 2 tau d tau, if we anti-differentiate that with respect to tau, we get 1/2 e to the 2 tau for v. So those are the ingredients for the calculation of that integral using integration by parts. So here I'm using the standard formula for integration by parts for a definite integral. My upper limit is t, my lower limit is 0. And then the next step I just plugged in what I found up above for u and v. And so this part, the integration is already done there. We just have to plug in. And for the second part, as usual, when we're doing integration by parts, we still have to do a little bit of integration here, but that's a fairly easy integral now for us to do. In the next step, I think maybe I'll look at the second term first. In the second term, I just anti-differentiated e to the 2 tau with respect to tau, and that gave me another factor of 2 in the denominator. So e to the 2 tau over 4 is my antiderivative, and then I just plug in t and 0 into that. It's a little bit more complicated maybe to see what happens when we plug in the first part. Keep in mind our integration variable is tau. So this upper limit t, what we're actually saying is tau is equal to t. So when tau is equal to t in this expression, that's just going to make that expression equal to 0. So we don't get anything at the upper limit when tau is equal to t. At the lower limit, when tau is equal to 0, we get e to the 0 or 1 for the exponential. So we just end up getting minus t over 2 when all is said and done with the first part of that expression. So that just gives us minus t over 2 plus e to the 2 tau over 4, which we haven't plugged in that part yet, but that's what's happening here. Then I just plugged in tau equals t for the upper limit and tau equals 0 for the lower limit. So that function of t there at the end would be the convolution of the two functions f of t and g of t that we were given at the beginning. Now there are some important properties of convolution that are listed in Theorem 1. We're going to look at the proof of property A on the next slide. The proofs of properties B and C are left as exercises. The basic idea here is with these properties is a convolution in some ways behaves like a kind of multiplication. Now, we're not saying it is multiplication, but we're saying it kind of behaves like multiplication in some ways. So property A tells us that convolution is commutative, just like multiplication is commutative. Property B tells us that convolution is associative, just like multiplication is associative. And property C tells us that convolution is distributive with respect to addition, just like multiplication is distributive with respect to addition. So here's a reminder of the definition of convolution, which we introduced in the previous slide. We're going to look at the proof of the first part of Theorem 1, the proof of the commutative property for convolution. The other parts of that, the other parts of that proof are left as exercises. So we'll look at the proof of Theorem 1a together. So here's a definition. F star g of t is integral from 0 to t, f of t minus tau, g of tau d tau. That's just copying from the orange box up above the definition of convolution. And to prove the result, all we really need to do here is do a little integration by substitution. So we let u be t minus tau, keeping in mind we're integrating with respect to tau, so we're thinking of t as being a constant. Then du is minus d tau. And our original limits of integration referred to tau. When tau is equal to 0, u is going to be equal to t. And when tau is equal to t, u is going to be 0. So that gives us this expression for the integral now with everything expressed in terms of u. And in a situation like this, when I have a minus sign hanging around, I usually like to use the minus sign to flip the limits of integration. So that's what I did here in the next step. So at this point we have f star g of t is the integral from 0 to t of f of u g of t minus u du. We're basically done at this point, but it may be a little more clear if I go back now to tau as my integration variable. That's what I'm doing in this step. Now that I'm done with the substitution, and it may be a little more clear what happens here if I go ahead and go back to use tau instead of u as integration variable. So that's all that's happening here, since it may be a little bit easier to hopefully see what happens with the result, since tau was what we used for the integration variable in the original definition up here. And of course this integral, if we just switch the order, since we know multiplication is commutative, I just reverse the order of the factors there in that integrand. And if we just compare that again with the definition up here, we see that's precisely the definition of G star F. So that's the proof that convolution is commutative. Now, the main reason convolution is so important is the convolution theorem, which is stated here. The Laplace transform of a convolution of two functions of t turns out to just be the product of the individual Laplace transforms. There is a proof of this in my book. I'm not going to go through the proof in this video, so you can look at the proof in the text if you feel like it. But it is kind of a strange looking result if you've never seen anything like this before. So before we go on, as a quick illustration of the convolution of the theorem of what it's saying, I want to go back to exercise 9e, which we calculated on the previous slide when I first was introducing the concept of convolution. In that exercise, we had two given functions of t. F of t is t, and g of t is e to the 2t. Now we know, of course, the Laplace transforms of those functions at this point. F of s, the Laplace transform of f of t, is 1 over s squared, and g of s is 1 over s minus 2 from our earlier work calculating known transforms of simple functions. In the solution of exercise 9e, we calculated the convolution and we ended up getting this expression for the convolution of those two functions. And now, as an illustration of the convolution theorem, I'm going to take the Laplace transform of that expression and see what happens. So here we're just Laplace transforming term by term in the usual way. The Laplace transform of negative t over 2 is minus 1 over 2s squared plus 1/4 times the Laplace transform of e to the 2t minus Laplace transform of 1. So that would be the Laplace transform of that function. And to get it into the form that we want, we need to find a common denominator. That's what's happening here. You do need to keep your wits about you here with the algebra. Your common denominator in that expression is going to have to contain a factor of 4. It's going to have to contain two factors of s, so s squared, and it's going to have to contain a factor of s minus 2. So your common denominator is 4s squared times s minus 2. And then you have three terms which you're combining in the numerator and fixing everything up. Fixing up the first term, you need to introduce a minus 2 times s minus 2. In the second term, you need to introduce an s squared. And in the last term, you need to introduce one factor of s and the factor s minus 2. So that gives you this expression in the numerator. And in the next step, a lot of things cancel out there. In that expression, you're going to have a minus 2s near the beginning and a plus 2s near the end, so those parts will cancel out. You're also going to have an s squared in the middle minus s squared near the end, so that's going to cancel out. So after all that cancellation happens in the numerator, the only thing you're left with in the numerator is 4. So that whole thing just boils down to that. Of course, we can divide out the 4, which is what we're doing in the next step, and then just breaking it up into those factors, and we see that we have indeed verified the statement of the convolution theorem in this situation. We took the Laplace transform of the convolution and we got the product of the Laplace transforms of the original functions that we started with. There are a lot of tricks that we can do when we have convolutions. We can come up with expressions for the solutions of differential equations in the form of an integral. And that's actually a very useful idea. That's one of the reasons why Laplace transform methods are important and why convolutions are important, as that can be a very handy way of thinking about the solutions of differential equations. In exercise 12b, I asked you to try and solve that differential equation using Laplace transforms. You're going to end up getting some kind of a convolution kind of a thing going on, and I left that as an exercise for you to try. If you need help with that, let me know. In exercise 12a, I thought it would be fun to go ahead and do that using good old first order linear solution technique, since this is a first order linear DE. So I'll go through that here. So P of t, the coefficient of y, is negative k, so your integrating factor is e to the minus kt. So we do the usual thing with first order linear DEs, multiply both sides of the DE by our integrating factor. As usual, we end up with the derivative of a product on the left-hand side. Here we're differentiating with respect to time. That's our independent variable here. And the next step, we're going to be integrating as usual. One thing that's a little bit different here, I thought it would be easier to follow the calculation if we use a definite integral instead of an indefinite integral. Usually at this stage when we're doing first order linear DEs, we use an indefinite integral on both sides, but I think this solution may be easier to follow if we use a definite integral instead. So I changed the variable in the previous step from t to tau, and then I just integrated both sides from 0 to t. That's what's happening here. Then on the left-hand side, we have the antiderivative of a derivative of a product is just that product. We're doing a definite integral, so we still have to plug in the limits of integration. Tau equals t and tau equals 0. And on the right-hand side, we're doing this problem in a very general way. The point is to come up with a formula that works no matter what the right-hand side function is. So we can't really do anything, can't do much with that since we don't know what the function f is. F at this point could be anything. The idea is it's some kind of external force or external voltage or something that's being applied to your system, and a lot of engineering problems, your system stays the same and you vary the external force or external voltage or something like that. And so thinking about the problem in this way will allow us to come up with one integral when we're done, and then we can just plug in whatever the right-hand side function we have, which we could vary if we need to, and just plug into that integral for our solution. So getting back to this solution in detail, in the next step on the left-hand side, we just plugged in tau equals t at the upper limit and tau equals 0 at the lower limit, and use the fact that e to the 0 is 1. And then we didn't really do anything here except just copy that part. In the next step, I guess I skipped a baby step here. I added y of 0 to both sides, and then I multiplied both sides by e to the kt. So I did skip one or two baby steps here. Basically, I'm just taking the previous expression and solving for y of t. So that gives me y of t is my solution of that initial value problem is y of 0, e to the kt plus something that looks a lot like a convolution. And so you should end up with something like that if you try solving that problem using a Laplace transform technique. And exercise 13D is a typical application of that type of formula. It fits the form of exercise 12A where k is -4 and your right hand side function is e to the minus t and y of 0 is 1. So one way to solve that, and by the way, this, I believe Mathematica and Wolfram Alpha may be doing something like this. I'm not sure about that, but when I check my answer in Wolfram Alpha, the form of the answer that it gave me leads me to believe Wolfram Alpha or Mathematica may be doing something like this for its calculation. In any case, if I take this formula now that we derived and as our solution to exercise 12A, that thing that I just underlined, we just plug in y of 0 is 1, k is -4, plus some kind of a convolution type thing, e to the minus 4t minus tau, times my right hand side function. My right hand side function was e to the minus t, so that gives me e to the minus tau there. And so we'll have our solution of that initial value problem if we just do a little bit of integration there. If you break up this part of the integral, you can pull out e to the minus 4t, and that's what I did in the next step. And that leaves e to the 4 tau, e to the minus tau inside the integral, which simplifies to e to the 3 tau for your integrand is what's left. So that's an easy antiderivative to do. That's what's happening here, anti-differentiating with respect to tau. And then in the next step, I plugged in tau equals t for the upper limit and tau equals 0 for the lower limit. And that gave me that. And now if we clean that up a little bit and just multiply out the second part and combine like terms, we see this expression for our solution of our initial value problem, 2/3 e to the minus 4t plus 1/3 e to the minus t.